All right, engineers, let's get into it. Today, we're doing a super fast revision on a topic that, well, literally powers our world: fuels and combustion. So if you're cramming for exams or just need a quick reset on the core ideas, you are in exactly the right place. Let's do this. So here's how we're going to break it down. We'll kick things off with the absolute basics. What's a fuel and how do we even measure its value? Then we're going to get into the nitty-gritty with two key analysis methods: Proximate and Ultimate. And we'll finish up with a handy checklist for what makes the perfect fuel. Okay, part one, fuel and combustion basics. Let's start at the very beginning with the fundamental reaction that honestly makes everything else we talk about possible. So what even is a fuel? At its core, it's pretty simple. It's any substance that can burn, and the main ingredient we're looking for is carbon. The whole point, the entire reason we use fuels, is that when you burn them the right way, they release a whole lot of heat. And that heat, that's the energy we need for, well, for everything. And this right here is how we unlock that energy. It's a process called combustion. All it is really is a chemical reaction, an oxidation reaction to be specific. You just take your fuel, add some oxygen, which we usually just get from the air, and what do you get? You get some combustion products like CO2 and water and, the most important part, heat. This super simple equation, it's the foundation for everything. Right, but as we know, not all fuels are created equal. Some are way better than others. So how do we actually measure that? That brings us to a fuel's real worth, its energy content. And this is an absolutely critical number for any kind of engineering work. The number one metric, the most important one, is its calorific value. All this means is the total amount of heat you get when you burn a specific amount of that fuel, say 1 kilogram, completely. It's really that simple. A higher calorific value just means you get more energy, more bang for your buck. Now, this is where things can get a little confusing. The difference between gross, or HCV, and net, or LCV. It all comes down to water vapor. See, most fuels have hydrogen, and when that burns, it creates steam. If you could somehow trap all that steam and cool it back down to water, you'd get back all the energy it took to make the steam in the first place. That's the gross value. It's the theoretical maximum. But in the real world, in most engines, that steam just flies out the exhaust pipe. So the actual usable heat you're left with, that's the net value. That's the practical reality. Okay, so we know we want a high calorific value. But how do we figure out the quality of a solid fuel, like a piece of coal? Well, let's start with the first method, proximate analysis. Think of this as the quick and dirty overview. Proximate analysis is a really straightforward lab process, and it's got 4 main steps. First, you gently heat a sample to get rid of any moisture. Step 2, you crank up the heat in a sealed container to release what's called volatile matter. These are gases that burn off easily. Third, you basically burn everything that's left until all you have is non-combustible ash. And finally, you get to the good stuff. The fixed carbon, the real powerhouse of the fuel, is just whatever's left over when you subtract the other 3 from 100%. And what does all this tell us? It tells us about the fuel's quality. You want really low moisture, because water just wastes energy turning into steam. You want low volatile matter, because that stuff tends to make a lot of smoke without giving you much heat. And you definitely want low ash. Ash is just useless filler that doesn't burn and can clog things up. So the goal is super simple. Get that high energy fixed carbon as high as possible and keep everything else as low as you can. So proximate analysis gives us a fantastic quality check, but it kind of lumps things into big groups. If we want to know the specific elements inside the fuel, we need to do a deep dive. And for that, we use ultimate analysis. This gives us the fuel's exact chemical recipe. And this is what ultimate analysis tells us: a precise percentage of each core element. How much carbon, how much hydrogen, how much sulfur, and so on. And why do we need this level of detail? Well, it's essential for things like super accurate design calculations, like figuring out the exact amount of air you need for perfect, efficient combustion. And every single one of these elements has a huge impact. Carbon and hydrogen? That's what you want. A high percentage is great because they're the main sources of heat. Sulfur, on the other hand, is a big problem. Sure, it adds a tiny bit of heat, but it burns to form sulfur dioxide, which causes acid rain and corrodes equipment. Nitrogen? It's basically just a filler. It adds 0 heat value. And oxygen is also a bad guy here, because it's already bonded inside the fuel, which actually lowers its total energy potential. Okay, so we've covered the basic theory, how to measure energy, and the 2 main ways to analyze a fuel. So let's pull all of this together and create the ultimate checklist for what makes a really good fuel from an engineering point of view. So here it is, the good fuel checklist. First, and this is non-negotiable, it's got to have a high calorific value. It needs low moisture and low ash, as we just discussed. Its ignition temperature should be moderate. You don't want something that's a fire hazard, but you also don't want something that's impossible to get started. The combustion has to be steady and controllable. And this is huge. It needs to produce minimal harmful gases. And finally, from a practical standpoint, it should just be easy to handle, store, and move around.
And that pretty much wraps up our revision. We've gone over the classic engineering take on fuels, but I want to leave you with one final thought. As we, as engineers, move towards a more sustainable future, how do you think this checklist might change? Will things like being carbon neutral or renewable start to outweigh pure calorific value? It's definitely some food for thought. Thanks for joining me.